Okay, folks, let's move on to the next part of this lecture, which is covering diode capacitance. So let's start off the bat, right off the bat, with asking ourselves, why do we even care about looking at capacitance for a diode? Well, there's two reasons. One, you understand that for circuits, the time response is dependent on resistance and capacitance, right? So you can look at the charging and discharging time, and ultimately you can never run a circuit faster than its RC time constant, right? How long it takes to basically get charged through the resistor to charge up a capacitor. So this is useful in terms of understanding how fast we can run circuits with diodes. The other reason it's important is every time you charge and discharge a capacitor, you consume electrical power, right? And so it's also important to understand capacitance from the perspective of electrical power consumed. We'll also see some advanced topics where if I use a diode, I can actually start to change capacitance dynamically and therefore make tunable circuits, which is kind of interesting, right? So, starting off with capacitance, let's not talk about diodes yet, but let's talk about something more general. Let's say I have a black box device, okay? I don't care if it's a shoe box with two wires coming out of it. I've got some sort of black box device with two wires, and I see that basically every time I change voltage on it, I see a change in charge. So I get a dQ for every dV. So the question is, does that black box have capacitance? Well, fundamentally, by the definition of capacitance, the answer is yes, because capacitance can be calculated as change in charge over change in voltage, right? More classically, that same box, if I basically were to increase a DC voltage and measure the charge on it, and I see a charge stored, I also would have a capacitance which I could calculate. So it doesn't matter what is inside the box, if it's a classic capacitor or a diode or whatever, so long as I see I get Q for V or a dQ for dV, I know I have a capacitance inside there. Now, we need to understand both of these, and we'll talk about both reasons for a diode, and we'll see that one's for forward bias, one's for reverse bias. We'll start with one which is a little bit simpler. We'll start with the one that you might have experienced in grade school when you made a capacitor, and they may have taken a piece of aluminum foil, a piece of paper as a dielectric, and another piece of aluminum foil as an electrode, and made a simple capacitor. Well, that simple metal dielectric metal capacitor, the capacitance can be calculated as follows, okay? Where I have the dielectric constants here, epsilon sub r, dielectric or permittivity of free space, the area of the capacitor, and the thickness of the dielectric. And so we'll find for a diode that this is something we'll call junction or depletion capacitance, and we'll also find for a diode that we also have something called storage capacitance, which is this more complicated dQ over dV, and that the total capacitance for a diode is this junction or depletion capacitance, two names, okay, and the storage capacitance. So let's first try to understand the junction or depletion capacitance, and I'm going to stick to the term depletion capacitance, okay, for now. And so this depletion capacitance is more of like a classic metal dielectric metal capacitor, okay? So looking at a diode, tell me where you think this depletion capacitance is, and where's my dielectric? Well, I've got conductive material here, I've got conductive material here, I've got insulating material here, and so basically this is my dielectric, this is my metal, and this gives me my capacitor, okay? So that's pretty simple to understand. And so let's try to derive this, because we already have great things to basically predict the width of this, which is part of what we need to calculate capacitance. And so go back to some of the formulas we had when we calculated Q on either side of a depletion region, right? We could do that. So this was for the N-type side where we dope it with phosphorus. This is the charge on that side. We have the depletion region width on either side. This would be depletion into the N side, Xn naught. And then we had the total depletion region width for the entire depletion region, which could be calculated as follows. Okay? So let's see if we can get our capacitance. So, starting with depletion capacitance, we're going to take our equation we had for depletion width, and in addition to contact potential, we're going to add in an applied potential. So I take the exact same formula, and all I'm doing is substituting in here an applied potential, which in this case is in the opposite direction of the contact potential. Okay? Now, remember, we could show for either side these relationships in a previous lecture, where this is the distance of depletion into the N side, distance of depletion into the P side. And we could basically rework things around for this using this equation, which was the charge on either side is equal, right? The charge on this side and the charge on this side are equal. So it says the charge on this side, the N-type side, is equal to the charge on this side, the P-type side, where this is charge coulomb, area, depletion into the P-type side, and the doping density on the P-type side. And if you do the units of this, you'll end up getting charge if you multiply all the units out. So if we combine these all together, we can end up with the following equations. We'll take all this and we end up with the following equation, where I have Q is equal to the charge of an electron coulomb, area, doping levels, times depletion width. Now, I want to substitute this equation here back into this equation for Q, and I'm going to recognize the following thing. Notice up here that I've got Na plus Nd over Na times Nd. And notice down here I've got the inverse of that, Na times Nd over Na plus Nd. Well, if I'm going to bring this down here, I'm going to call this, let's pretend that this is, let's say this is x, right? And I'll call this 1 over x then. Well, if I have 1 over x square root, 1 over x to the square root is equal to x to the minus 1/2, right? That's equivalent. So if I have x to the minus 1/2 times x times x to the minus 1/2 is equal to x to the 1/2. The point being is I can combine these two as just x to the 1/2, and then I bring the other terms and I put them out here in front here. Okay, so I basically inserted w into this equation. I'm showing you how I basically combined these terms using some simple math there. So I've done that. I've got a new equation here which gives me the charge, total charge on either side of the diode as a function of voltage and doping levels. Okay, so how am I going to finish this off? Well, it's going to be pretty simple. Remember, I can calculate capacitance, which is my goal, as Q over V, or C equals dQ dV. So now I've got an equation for Q. So if I know that capacitance is dQ over dV, and I have an equation which gives me Q as a function of V, then I'll just take the derivative of this with respect to voltage, right? And that will give me my capacitance. So I take this equation, I take the derivative of this with respect to voltage, that will give me my depletion capacitance or junction. They're the same term, remember, so I call it CJ, but I tend to call it depletion capacitance. And as I take the derivative, of course, of this with respect to voltage, I go derivative of something to the 1/2 gives me to the minus 1/2 power. The 1/2 falls out, so that's where I get this over 2 here. This is what I'm taking the derivative of, so this term stays. And this stuff here is just a constant that stays out in front of the term. So now I've got the capacitance calculated here. What I'm going to do next is recognize that something to the minus 1/2 is the same as that same thing to the 1/2, so I've moved this back inside here. Then I'm going to pull out some of the other terms, okay, inside here. So I notice that I can pull out this by putting 1 here and then 1 here as x to the, x and x to the minus 1/2 is same as x to the 1/2, right, I'm sorry. I can recognize that x to the 1/2 is the same as x times x to the minus 1/2, so I was able to pull this out and put this in the denominator. Then I'm going to recognize that this whole term right here is just the W I started with, the depletion region width. I'm going to put W back in here, substitute this out, and I get the following equation for depletion capacitance. My depletion capacitance is dielectric constant of the silicon here, the area of this, the cross-sectional area, divided by the width of the depletion region. This should make complete sense, and all we did was show a derivation that indeed this is just a dielectric metal parallel plate capacitor, and this equation allows us to calculate the capacitance. And so all this was just a derivation to prove what we had expected already. If you want an example W, here's an example for 10 to the 18th p-type, 10 to the 15th for n-type. You get about 0.5 microns, and then you could substitute the other values in there and figure out what the capacitance would be for a given area. Okay, so with this depletion capacitance, if you look at how this changes with voltage, as you put more and more reverse bias voltage on a diode, the depletion region gets bigger, right? And as you start to forward bias a diode, the depletion region gets smaller. And so if the depletion region width gets smaller, my capacitance should increase. If my depletion region width gets larger, right, then my capacitance should decrease according to the equation we have. And so if I plot capacitance versus reverse voltage, as I go to more and more reverse bias, the capacitance decreases because my depletion region width is getting bigger and bigger. Okay? So, there's a couple of interesting things about this. The first thing that's interesting about this is that I could design a diode for a strong capacitance change, and those are called Varactor diodes. Why is that called a Varactor diode? Well, the main reason is that you get a tunable reactance. So remember, impedance I can measure as Z impedance is equal to resistance plus 1 over omega C, where C is the capacitance, and I put my frequency here into omega, right? R is the resistance, and 1 over omega C is called the reactance. And so if I have a variable reactance, because I'm able to tune capacitance, then I can call this a variable reactance or Varactor diode, and I have this elegant tunable capacitance component that I can put into a circuit. So let's say you have a circuit where you've got a tuned capacitance and you don't want to do it with like some sort of mechanical component. You could put a diode in there and simply change the DC voltage on the diode and change the capacitance seen in part of a circuit real time. This is really helpful for things like antennas and transmission lines, because when you get to those subjects in signals and systems and in electromagnetic fields, you'll see that having the properly tuned capacitance is critical for getting maximum transmission of a high frequency, radio frequency, or microwave signal along a transmission line, or getting an antenna to emit at maximum efficiency of the frequency you want. You have to have the exact right capacitance. Well, you put one of these tunable Varactor diodes in there, then you are able to tune this thing real time so it hits its sweet spot, and it's basically propagating an RF or microwave RF or microwave signal with maximum efficiency. We can also simplify this down, and we'll see why this is important in a second. So most of the time in this class, we said we'll have P plus N diodes, right, or N plus P. Again, most of the time, and I'll explain this when we talk about fabrication, you'll see that one side's heavily doped and the other side's lightly doped. Well, if I do that, I can simplify this down. So if this is P plus, right, Na is much greater than Nd, and so this just becomes Na. So I can get rid of Nd. Then I end up with Na over Na, which cancels out, and I end up with just Nd. And so this simplifies to just Nd. And you see that your capacitance here, depletion capacitance, is a function of voltage and N-type doping. And that makes sense because if this is heavily doped, all the depletion width is into the lightly doped side. And so I can modulate most of the depletion region width by just changing the N-type doping. This is also important because what I can do then is, you've never asked me in this course, if you dope a semiconductor, how do you tell what the doping level is? How do you measure it? If I took this type of diode and I basically changed the voltage applied and I measured the capacitance on it, I could then back calculate the doping level because I know Q, I know these are all constants, right? I could measure the area by looking at the area of the electrical contact I made, and I could get multiple measurements of capacitance versus voltage, which would give me multiple confirmations of the value I should have for doping level. So this is a really nice way to electrically measure doping level for a diode. Now, notice that if the applied voltage gets close to the contact potential, meaning you're starting to forward bias this, the capacitance gets really large. And we'll talk more about that in a second. Here's a spec sheet for some Varactor diodes. Let's just kind of look at it here. They give you the, what's this here? Oh, this is the breakdown voltage, so don't take it beyond minus 16 volts. So that's as far as reverse bias as you can take it. And there's the reverse saturation current, okay? And here's the capacitance as you put more and more reverse bias on this. And so this is in picofarads here, right? Here's the minimum and the typical. Let's just look at the minimum, for example. You have a low reverse bias, you get a large capacitance. You go to 8 volts of reverse bias, the capacitance drops by more than an order of magnitude. So you've got a simple component here which you can tune over an order of magnitude, the capacitance, and tune it electrically, which is a very useful tool for circuit design and modification. Okay, let's see. Anything else? That's enough for this one. Okay, now let's go and take a look at the second type of capacitance we talked about, storage capacitance. So we just derived an equation for depletion capacitance, right? Which is a classic metal dielectric metal type capacitor. Well, that was for reverse bias mainly. It turns out in forward bias, typically storage capacitance dominates. And so why would I have a different type of capacitance in forward bias? Well, remember, for a diode, indeed, when you basically change voltage on the diode, you start pouring charge over to the other side, right? And so if I change the voltage a little bit, the amount of charge pouring from one side to the other changes substantially. And remember, when you pour the charge over to this side and the charge over to this side, these holes become minority holes, these electrons become minority electrons, and in reverse bias I have reduced minority carriers, and in forward bias I build up an excess of minority carriers on either side. And so I can already see that I'm getting a dQ in terms of the minority carriers changing for a dV. So let's see if we can figure this out in terms of already what this would be in forward and reverse bias. So, first question, when I reverse bias a diode, will I have a storage capacitance? Well, we know for a diode that the reverse bias current does not change with voltage, right? And so I could have a dV, but I'm getting no dQ, so in reverse bias I get no storage capacitance. I only have depletion capacitance. In forward bias, I know I get a huge change. If I change voltage, I get a huge change in current, which means I've got a large change in dQ for my dV, and so for forward bias, I do get a significant storage capacitance. Let's take a look at this one step further and ask ourselves, how might the storage capacitance change in forward bias? Well, the storage capacitance right here, here's my dV. Let's say I'm going from right here. There's my dV back and forth, right? And then there's how much current is changing, right? And so I get a decent amount for a given dV, I get a decent amount of dQ, right? Look over here. Let's go the same amount of dV here, okay? So I'll draw this down to the best of my ability. Same amount of dV here. So there's my dV, here's a dV, same amount. Now look what happened. My dQ, essentially, right? My dQ is huge. And so what this is showing me is that my storage capacitance increases substantially as I increase the forward bias on a diode. So it's going to shoot up because I'm getting a larger dQ for a given dV. Let's look at. So again, forward bias, I get excess minority carriers. Holes this way show up as excess holes, and as I go deeper into the N-type material, they recombine, right? And these holes are adding up to the normal background concentration of minority carrier holes in the N-type material. Electrons diffusing this way, they show up on this side. I get an excess at the interface, adding to the normal background concentration of thermally generated minority electrons here, and as I go further distance into the P-type material, those electrons recombine such that I get back to the normal thermally generated concentration. But the point is, forward bias, there's my dQ. See that? That's an excess. There's a dQ there. I get an excess, okay? Now, for reverse bias, I've changed the charge right near the edge. Remember that all the holes sitting near the edge of this depletion region, okay, I'm sorry, this is electrons. All the electrons near the edge of the depletion region drift across, right? So if I've got, here's my diode, and I'm on the P side, so I'm over here, and I'm a minority carrier electron right here, right? It's right near the depletion region edge, and it drifts across. So every electron right here at the depletion region edge drifts across. So here I am, I'm looking at the electron concentration at the depletion edge, and it goes to 0. Every electron right at the edge will go across. Only when I get further away, way out here, do I see my normal thermally generated electron carrier concentration. The key point again is that this curve here does not change with voltage, right? And so yes, I get a dQ for a dV, but it doesn't at first, but it doesn't change with further reverse bias voltage. Once you get to reverse bias, you get this type of profile. So I'm not going to calculate storage capacitance for a reverse bias diode. So let's use what we have here, and we'll basically figure out our storage capacitance for forward bias in a little bit more. So I said we'd figure it out, but it's actually a little bit more complex than what we have time for, and which is of use to you. So if you were to calculate your storage capacitance, okay, and by the way, another term they have for it is called diffusion capacitance. You could calculate that, and you would get the following prediction for storage capacitance versus forward bias. You would see all of a sudden at some forward bias, your diode turns on, and your storage capacitance shoots up substantially. Now, be careful. It shoots up, and this is much greater than my depletion capacitance, but there's a couple effects that happen. First off, you get to a certain point, it goes back down. Okay? That's beyond what we can cover in this course. The other thing is that the only time we get storage capacitance is for something called a short diode, which we always have in this course typically. If you have a long diode where the diode is so long that it doesn't pinch the excess profiles like you see here, then you actually get no storage capacitance. I don't want to confuse you, but here's the main thing I want you to remember, okay? So this is, what I've given you here is just for your own benefit, but the main thing I want you to remember is that for the most of the diodes we have in this course, we will find that the storage capacitance increases exponentially with forward bias voltage, and it will dominate over the depletion capacitance. It's interesting that, in this course we talk about silicon, but these sort of capacitance show up in any type of diode device. So it turns out that OLED displays, organic light-emitting diode displays, which are some of the new displays you're seeing coming out in smartphones, are made out of diodes, right? It's called an organic light-emitting diode display. And so here's a paper. I was looking at some papers, and I found a paper where they were talking about storage capacitance in a diode. And so they measured the capacitance versus voltage, and they found that when they reverse biased it, the capacitance went down because you're looking at depletion capacitance and the depletion region's increasing. But importantly for this, when they went to forward bias, they saw that storage capacitance go up, it starts to shoot up, and then it goes down. But the main point is that when you go to normal forward bias voltages, the storage capacitance increases. And so it's interesting, they say that in the paper, I pulled this quote, they infer that the phenomena resulted from an extremely thin OLED structure, just like short PN semiconductor diodes. And we'll talk more about OLED materials later in this course, so you'll start to understand what are these things here and why is this different than silicon. But the point being that what I teach you in silicon applies beyond silicon as well. Okay, last topic, and then we're done with capacitance. This is another topic which I'm not going to lecture in detail on because it's beyond the scope of this class. But I want you to be aware of it also, such that if you see it in an electronics lab or something like that, it won't be a complete mystery to you, okay? So, when I forward bias a diode, I end up building up excess charges on either side, right? And so if I forward bias a diode, and on this side I'm building up a bunch of extra electrons, like you can see over here. On this side I'm building up a bunch of extra holes. Let's switch colors there so I could draw the holes a little bit. Well, anyway, yeah, I can switch to green. So on this side I'm building up a bunch of extra holes, okay? I did a really bad job with that. Sorry. Anyway, let me try it one more time here. On this side, I'm building up a bunch of electrons. On this side, I'm building up a bunch of holes. Okay? So I forward bias it. Electrons go this way. Holes go this way. I build up an extra dQ on either side. Right? So I've got a dQ that's built up on either side. Well, my point is that here I am in forward bias for voltage. So forward bias for voltage. Let's say at t equals 0, I go straight to reverse bias. Well, when I go to forward bias to reverse bias, it's going to take some time for all of these charges to recombine. So what you're going to find if you actually go from forward bias to reverse bias for a diode is that if you look at the current, not the voltage, here's voltage versus time, the current versus time will look like this. Here's my forward bias current. I reverse bias the diode, and I see I get this spike for a short period of time, which is corresponding to the time it takes for these charges to recombine. Because as these recombine, I need to bring in charges to recombine with them, right? And so I get a current here for a storage delay time, TSD, which accounts for the time it takes for the excess I build up in forward bias to recombine. Then only after that does it go down to the normal reverse saturation level for current, which is really small. So again, here's a big current, right? This is a big current here, forward bias. Here's my reverse saturation current on this scale of current. It's very small, but when you go from forward to reverse, you're going to see this current spike at first, which is the time it takes and the current it takes to bring in charges to recombine with the forward bias charges you build up on either side of the diode. If you don't fully understand how all of this works, there's some extra slides at the end which you can check in the PowerPoint and PDF. And again, if you want to understand the storage delay time, here's some simple ways you can calculate it based on carrier lifetime, forward current, and the reverse current for a diode. And it's typically 0.1 to 10 microseconds is how long this takes before you get to your typical reverse saturation current. Okay, so that's it. I know some of this stuff was a little bit more complicated, and I couldn't go into full detail on all the topics, but you should be absolutely certain that you can answer these questions here. These are the ones you really need to take home, and you should be able to use the equations we have to calculate capacitance, especially for reverse bias, which is depletion capacitance.